All right, folks, so let's get started. We are forging ahead with chapter 16. I hope to finish it today. We're going to be doing a lot of calculations, so if you have get your calculators out, that would be great. So we left off talking about pH calculations, and so how to navigate these different equations here. That P is just a function that means negative log of something. So pH is negative log concentration of H plus. pOH is negative log concentration of OH minus. We will see things like pKa. That is just the negative log of your Ka value that is there. So it just allows us to work with these really small numbers because like H plus and OH minus, those are typically really small numbers. So when we report it in a pH scale, we see whole numbers that look nicer to our eyes than like tiny numbers. And so going from concentration to pH, we do the negative log. To undo it, if we are given a pH and want to know H plus concentration, we take 10 to the negative whatever that pH value is, will give us the concentration within there. So that's how we express things that are acidic versus basic using our pH scale. And what we say, at 25 degrees Celsius, pH equals 7. That's our neutral point. Only when our temperature of our water is 25 degrees, because our kW is 1 times 10 to the negative 14. And so at 25 degrees Celsius, pH 7 is neutral. The thing is I think we did an example where, okay, if at 50 degrees, kW changes a little bit, because this is the kW expression is a endothermic process. kW changes a little bit. It shifts these X values. Because concentration of H plus is still equal to concentration of OH, the sample is still neutral. But if you would measure the pH, it would actually be slightly less than 7. Don't let your mind trick you and think, oh, hot water is acidic. It's not. It's just the point at which H plus and OH is the same concentration, so neutral. It just so happens to happen at 6.63 at these hotter temperatures. So what's our physiological body temperature? Does anyone know? In Fahrenheit, it's 98 point whatever. Yeah, so if we changed that to Celsius, we would see a kW slightly more than 1 times 10 to the negative 14. And so what will happen is that shifts the neutral point in our bodies, because we operate at a higher temperature, slightly closer to this pH point, like 6 point something instead of 7.0, what we are used to. But I will say 99% of the time, when we're doing questions in this class, we're going to assume it's 25 degrees Celsius. So the whole idea, neutral is 7.00, pH plus pOH is 14. That will work basically all the time unless I say otherwise. Like if I have a specific question that says, consider water auto-ionization at this temperature, and I give you the new kW. We're going to assume this is always true, since we're doing just benchtop chemistry. All right, so because we're doing logarithms and log base 10, we went over sig figs. The big idea here is when you get a pH value, that whole number in the front doesn't count in your sig figs. So if your molarity your concentration has 2 sig figs, your pH needs 2 decimal places. And the opposite is true. If you are given a pH value with 3 decimal places, so the number out front doesn't matter. That just tells you the magnitude of the your scientific notation. If it has 3 decimal places in your pH, your concentration needs 3 sig figs. Okay, so that's how that works. And so we did a couple examples. Let's just do some calculations. So in all of these examples, these are all strong electrolytes, meaning strong acids, strong bases. So if we have a strong electrolyte in solution, it means when we dissolve the thing, it's all ions. So the idea here is if we want pH, we need H plus concentration. So in the first one, we have a concentration of HCl. Where does my H plus come from? From HCl, because it's a strong acid. That's what I want you to recognize, all right? That in this example, because H plus is a strong electrolyte, H plus concentration is also equal to the HCl concentration. So it's equal to 0.025 molarity. The only reason I'm writing this for strong acids and bases is because it changes when we go to weak acids and bases. We can't say this for a weak acid or weak base. We can only say it for strong acids and strong bases. So for now, we can do the simple calculations first. So we have H plus concentration. How do we get pH? Negative log it. Okay, so how many sig figs will my pH have? How many sig figs will my pH, or not sig figs, how many decimals? 3 decimal places, right? So pH in this case is negative log 0.0250. And so that number in your calculator, will be 1 point, and we said 3 decimal places, so 602 pH. All right, the next one, pH of a sodium hydroxide solution. So thinking about when you dissolve sodium hydroxide in solution, you get, and it's a strong electrolyte, a strong base, you get sodium ions, you get OH ions. So the idea here is, in the previous one, it was an acid, I can just get H plus, but in this case, because it's a base, I can get OH concentration. It is equal to our sodium hydroxide concentration, which is 0.0175 molarity. I can take that number. If I take the negative log of that number, does that give me pH? No, it gives me POH. And then you just do 14 minus that, and then you got your pH, all right? So this way, we do it a little bit differently. So POH equals something, equals 1.75. How many decimal places do I want to go out? 3. So 1.757. And so pH is just 14 minus that number. And so our pH is 12.243. All right. So there we go. Another way you can get H plus concentration, so this is another way you can do it, is recognize that Kw equals H plus times OH minus. And so since we have the OH minus value, that one, we can calculate H plus. Kw is 1 times 10 to the negative 14. So you can go ahead and straight get H plus concentration, then plug it into the negative log thing. It's actually the same exact thing. When we say pH plus POH equals 14, it's the same thing as we just took the negative log of Kw on both sides. It's actually the same equation, as long as Kw is 1 times 10 to the negative 14. All right, so the next one, what's the pH of this solution? So similar idea from the previous ones, we just want to get H plus concentration, but in this example, it's probably better to, instead of calculating H plus straight off the bat, we want to get the concentration of OH minus, because this is a hydroxide. All right, the only difference here is, so calcium hydroxide is a strong electrolyte, so for every 1 mole of calcium hydroxide, like substance we put in water, how many hydroxides do we get out? 2. So the OH concentration isn't this number, it's this number times 2. Okay, good. Good. So, but to write out the work, okay, so we again want OH minus concentration. It's going to be equal to 2 times the calcium hydroxide concentration. So what is that? 0.0060 molarity. And then I'm going to put that number into my negative log thing. And so I get POH is equal to 2.2, how many sig figs? Or sorry, how many decimal places? 2 decimal places, so 2.22, and so therefore pH is equal to 11.78. And again, a good thing is use your intuition a little bit here. You added a base to solution, right? Calcium hydroxide is a base. You would anticipate the pH to be basic. Is this pH basic? Yes. So do make sure, use your intuition a little bit with a question, right? Like you added a base, the pH should be basic. In the first one, we added an acid, so the pH should be acidic. Is it acidic in the first one? Yes, so that's just something like you can take half a second to check yourself to make sure that you're reporting the correct number. Okay. All right, last one. So what is the pH of this sulfuric acid solution? So sulfuric acid is a strong electrolyte, but do you remember in Chem 1210 when we talked about this, sulfuric acid being a strong electrolyte? See how there's 2 hydrogens there? And we might be really compelled to say, oh, 2 hydrogens pop off, but that's not how it is. It's a 2-step process. Yes, so I'm not sure if you remember this from 1210, but we said that only the first hydrogen is strong for sulfuric acid. So our H+ concentration is actually just that number. So this is analogous to HCl, essentially. It's a monoprotic strong acid. Only that first H+ is strong. And I put it right next to calcium hydroxide to like purposely trick you. So you might think that there's 2 there, but there's not. There's just 1. That first hydrogen is strong and fully dissociates. So in this case, H+ is just equal to that 0.0050 thing, right? And so just plug that into pH, and you get that the pH is 2.30. So only that first hydrogen is strong in that case, even though there's a 2. Like both protons are acidic, but only the first one is strong. All right. Unlike calcium hydroxide, where the whole thing's ionic and the whole thing just breaks apart into its ions because it's a strong electrolyte. Okay, so let's just check ourselves here. I want to do this demo. So let's just, I'm going to introduce it and then we'll get to the rest of it later. In the first one, we saw when we add HCl to solution, we got an acidic pH, right? Add an acid, the pH goes below 7, it becomes acidic. So I have a bunch of different things here, and we're going to test their pHs, but I want us first to make the simple observation of predicting the pH when we add certain substances. So HCl is an acid. I have an indicator here that changes color based upon the pH of the solution. So here I have HCl. We predict it's going to become acidic when I add it. So I'm going to add a couple drops. So it's right now, do you see it's green? So this is the color it is when the pH is 7. So now I'm going to add HCl. The pH is going to go down. The color is going to change. I don't know what color it's going to change. I've never done this. So there we go. Do you see it? So that's the color of HCl. So when it's acidic, it's this color. And we'll compare. We need to make these references anyway so we can figure out the pHs of other things. Just know that this is the color when it's acidic. So you can imagine we're going to do the same thing, but instead of adding HCl, we're going to add sodium hydroxide. So like a base, all right? So right now this is neutral. I add a base, the pH is going to go up. The color is going to change. I don't know to what color it is. She said a couple drops, but I just added a bunch. Okay. Ooh, that's a pretty color. Do you see that? See that? So that's the color when it is basic. So I'll remind you, it's acidic on that side, basic on that side, and we'll test a bunch of different substances in a little bit. All right, we add a base. It should become basic. In a little bit, when we get to chapter 17, I get to tell you that I lied to you, and we'll look at some really bizarre scenarios. Okay, all right. So just remember that. When you add an acid, it should become acidic. When you add a base, it should be basic. I can't wait till we get to chapter 17. It's fun. It's a lot of calculations. All right, let's do a couple more. All right. We throw a large scoop of barium hydroxide, right, BaOH, 2 of them, into water, but not all of the solid dissolves. That is what? Saturated. That's a saturated solution, if not all the solid dissolves. If I tell you that at this temperature, the solubility of barium hydroxide is 0.1077 moles per liter, meaning that's how many moles of barium hydroxide will dissolve in 1 liter of water, That's the solubility. Calculate the hydroxide calculation or concentration and the pH of this saturated solution. So this number, the 0.1077 moles, that's essentially molarity, is telling you the concentration of barium hydroxide. This question is really no different than this calcium hydroxide question. It's just because this is a saturated solution, you need to recognize that that concentration given is the concentration of the solution. It's how much barium hydroxide actually dissolves in the water, right? So let's calculate the OH concentration. Is that concentration the OH concentration? No, it is, the OH is actually 2 times because you get 2 hydroxides for every 1 of those barium hydroxides. So it is 2 times 0.1077 molarity. So that equals, I don't know, 0.2154 molarity. So that's hydroxide. And so to get pH, I'll get POH first. Does that sound good? And then go to pH, because yeah, it's at 25 degrees Celsius. So this is POH is 0.66. How many decimal places should I have for POH? 4, yeah, so a lot of them. So 6668. And then so pH is equal to just 14 minus that, so 13.3332. Does this match our intuition? We added barium hydroxide, a base. The pH went up. It's basic, yes. Okay, so let's take that a little bit further here. Okay, so what if we removed a liter of that solution, of the saturated solution? So we just removed it off the top. When we remove the just solution off the top of the saturated solution, do we change the concentration at all? No, we don't. And then we take that 1 liter of solution and we dilute it a little bit. So once we dilute it, do we change the concentration? So I'm removing the solid. So if I take away just the top solution, I'm not taking any solid, right? So I'm only taking a certain amount of moles of solution. If I add more water, because there's no solid at the bottom, I just dilute the whole thing. So that's the idea here. I'm basically saying, hey, how does the pH change if we dilute some of that concentration? So the idea here is we're using our M1 V1 equals M2 V2 equation, but we need to be very careful in how we label these different variables. So 1 liter of that saturated solution, to me that sounds like V1. That saturated solution had a certain concentration, right? The OH concentration is equal to 0.2154. We already said that. So that to me sounds like M1. V2 is V2 500. Yeah, use your reading comprehension. What is V2 actually? V2. What's our new volume? If we start with a liter and we add 500 milliliters, what's V2? 1.5, yes. So V2 equals 1.50 liters. And so here, once we figure out what is M2, right, M2 will give us, okay, what is that final OH concentration after we diluted it, then we can get POH, right, and get pH that way. So if you plug in all these numbers, I'll just do it. V1 is 1 liter. That was V1. M1 is 0.2154 molarity equals M2, that's what we're calculating, and V2 is 1.5 liters. So in this case, M2 equals some diluted concentration, so it's going to go down, 0.1436 molarity OH. All right, and so again, because this is no longer a saturated solution, we just took liquid off the top and diluted it, there's no solid there to essentially bring that concentration back up to saturation. So that's the idea there. So that, going back to chapter 13 stuff. All right, is that my answer? Is M2 my answer? No. So to get pH, I want to get POH first. And so that is, if I take the negative log, is 0.84. How many sig figs should I have? I should probably only have 2. So 0.84, so pH is equal to 13.16. Okay, so let's compare that here. So we had a more concentrated pH, or concentrated OH. It had a basicity, it was 13.3, but then we diluted it, lowered the OH concentration, and we see that the pH went down a little bit because we diluted it. We decreased the concentration of OH particles in solution. All right, so, let's do one more. Let's calculate the pH of a mixture formed by 500 milliliters of HCl, 125 milliliters of HI, of that much HI. So the idea here, just like the other ones, is we need the H plus concentration. But the problem is here is there are 2 sources of H plus. Do you see the 2 sources? There's HCl and there's HI. So if we can just figure out, okay, how many total moles of H plus are there? That's what I'm going to plug into my pH calculation. So simply, this is basically a dilution equation where M total V total is equal to the molarity of HCl times the volume of HCl plus the molarity of HI plus times the volume of HI. What I'm basically saying is, hey, the moles of H plus total equals the moles of H plus from HCl plus the moles of H plus from HI. That makes sense, right? Like that's the total moles. So that's what this equation is basically saying. This is kind of like a modified dilution equation, but with multiple components. That's why I like to think of it. All right, so putting this all together, you get that the moles of HCl total is equal to 0.20, the HCl one, so molarity times 50 milliliters from HCl, molarity of HI, so 0.010 times 125 milliliters from HCl. But what is V total here? What's V total? Reading comprehension. Is it 50? Is it 125? 175, very good, 175. Okay, and so what you get here, I left out everything in milliliters because you can convert it to liters and then you have to convert everything to liters, but then they all just end up canceling out. So you can leave it in milliliters here. You get that the total concentration of H plus is 0.0128. I think there should be 2 sig figs, probably. Molarity H plus. And so once you throw that into your pH calculation, your pH is equal to 1.89. So there's another way I can ask a pH calculation. And so from now on, when I have an H plus concentration, go to pH, it's just the negative log of that number. I'm not going to spend time writing out negative log of it over and over. You know that those 2 numbers, they mean the same thing, just one has that negative log function attached to it. Okay, because we're going to be calculating pH all the frickin' time for the next 2 weeks. How do we feel on that? Good? Okay, so, last one, okay. So here we have a really low pH, it's really acidic. So let's ask ourselves, can we have a negative pH? Just think about it. I don't want you to see the answer. Do you think we can have a negative pH? Does that sound intuitive? To me, it does not sound intuitive. Okay, oh no, negative pH, no. I guess close to 0, that's as acidic as you can get. But let's just recall what the pH calculation, what that formula is. pH is equal to negative log of H plus concentration. So Let's calculate the pH of concentrated HCl, which I'm sure you used in lab, probably, I hope, with gloves on at one point, all right? This stuff is 12.1 molarity. So put 12.1 in there and tell me what you get. What do you get? Negative 1.36, so 0.83. So yes, you can have a negative pH when your H plus is super concentrated, when it's super concentrated. But the thing is that like we rarely ever work with really concentrated solutions in this case. All right, so it'll be rare to see a negative pH. You can also have a pH above 14. That means you just have a really, really concentrated hydroxide concentration. So thinking back, what would a pH of 0 be? What H plus concentration would that be? If you measured a pH of 0, what HCl concentration? No. Remember 10. So remember how we go from pH to H plus. H plus concentration equals 10 to the negative pH. So if pH is 0, you were close. 10 to the negative 0 or 10 to the 0 is 1. So a molarity of 1 would give you a pH of 0. So that's just to like reference yourself. We oftentimes in lab when we're working with acid solutions, are they usually greater than 1 molarity? No, they're usually really, really small. Like if you remember like our titrations, they were always like fractions of a molarity. So the pH isn't super, super concentrated. All right, but once you talk about like concentrated HCl, heck yeah, it's like super concentrated. Okay, all right. So those are strong acids and bases, relating that to pH. The idea there is it completely dissociates. When we have HCl dissociating in water, behaving like an acid, what kind of arrow do we use to like show H plus and Cl minus? Like a full-blown arrow. We're trying to show people like, hey, it completely dissociates. Versus a weak acid, weak base uses the double arrow, where we have to use like some type of Ka or K expression to say what's the ratio of products versus reactants. That's the next part we're going to go to. We have to do ice tables now. But the nice thing about these ice tables is that you almost always can make an approximation. Almost always. Okay, all right. So we did strong acids, strong bases, right? pH equals negative log H plus. These calculations were straightforward because, you know, in HCl, all of it goes to H plus, but in weak acids, weak bases, it does not. That's the problem. So we need to consider Ka, that equilibrium constant, before we can plug them into a pH concentration. All right. Oh, okay, yeah, so I got ahead of myself here. Okay, so let's just review strong acids versus weak acids. HCl, for example, when we show it reacting with water to be an acid, right? Our products are H3O plus aqueous and Cl minus aqueous. We use a like fully forward arrow to show, hey, all of it dissociates. Versus a weak acid like HF, we use a double arrow. It still dissociates, but only partially. And so this is what we get. So the products look analogous, right? We have acid and the conjugate base, but the difference is in a strong acid, when we put HCl into water, all we see are products. So if we pretended to calculate K would be like closer to 0 or infinity. If we tried to calculate K for a strong acid or a strong electrolyte, if only products exist. If only products exist and you calculate K is what's on the numerator? Products over reactants. So where's that infinity? Is it on the top or the bottom? The top. So if we calculated K, it would be infinity for a strong electrolyte. That's the big idea there. That's That's why you'll never see a strong electrolyte on the Ka table, because it's infinity. Versus something like HF, since it's a weak acid, both the product side and reactant side exist, so Ka is actually a number, that like a ratio. So the idea here is Ka is infinity for a strong acid, but then Ka like is a number within here. So if for HCl, when we have this full-blown arrow, in which of these reactions produces more H+? If we have the same concentration. HCl, it's a strong acid, right? This is a Chem 1210 question. It was like, if you had 1 molarity of each of these, which one conducts more electricity? What did we say? It was the strong electrolyte, so HCl. It produces more H+, it produces more products. So there's one idea here, comparing a strong versus a weak acid. Now let's compare the conjugate bases. So here I highlight the conjugate bases, Cl- and F-, okay? Which conjugate base is predicted to be more basic? Remember the rules for acidity. The stronger the acid, the weaker the conjugate base. That HCl is so good at donating AH+, its conjugate base is really lousy at taking it back. Versus something that's like not very good at either can both like donate an H+ and take it back. So that's what HF is. So which conjugate base is more basic? F- is more basic because it's the weaker acid. Okay, HCl is essentially so strong, all right, it's going to donate that proton and never take it back. So Cl- is not basic at all. And that's the big idea here. So F- because HF is weak acid. Okay, so the big ideas here with our strong electrolytes, strong acid, strong base, their conjugates, they either lose their protons or take protons, but they can't do it the other way. It's so strong, it's like the opposite can't be true. They're only good at doing one thing and one thing only. So that means their conjugates are not acids, they're not bases, they're actually just salts. And this is important when we go on to start predicting the pH of the acidity of different salts. If we know that idea, anything with a chloride is not an acid, it's not a base because HCl is a strong acid. Versus weak acids and weak bases. A weak acid is a weak acid, it has a Ka, so if you look at its conjugate base, it is a weak base as well. Or if you look at a weak base, add a proton to it to get its conjugate acid, that conjugate acid is also a weak acid. So there's a lot of different ideas here, and it will bring us into the concept of buffers in chapter 17, where we have both an acid and its conjugate, or base and its conjugate in the same solution. All right, and so the idea here, stronger the acid, weaker the conjugate base, stronger the weak base, weaker the conjugate acid. So there we go. All right, so let's keep going. Oh, and so here's what the solutions would look like, right? HCl, everything is dissociated, all ions, versus a weak acid. See how there's some neutral molecules still there, and some ions. So both sides of the reaction exist, and see how the arrows matter here. All right, so let's review weak acids and the Ka for them. This K is the same K we've been using for the past since chapter 15. So here's the general equation for a weak acid. We can also just write it this way because chemists are lazy. All right, and all these are aqueous. So essentially what I'm doing is just dropping the water part out. And you recognize that H+, a proton, is the same thing as H3O+. This hydronium ion is what H+ exists as in water. Like if I went in here with spectacles and like looked at it, it would be H3O+. H+ actually doesn't exist freely in solution, but I'm lazy. And I write it this way because what you'll see if you write the Ka expression, they're the exact same. Like let's write the Ka expression for both of them. So Ka is products over reactants, but only things that are aqueous. So do we include water? No. Okay, so let's write it. So for like this reaction, H3O plus times A minus over HA is our Ka expression. Or for the second one, the lazy way, is H plus times A minus over HA. And so they're essentially the same. They're the same equation. You just have to recognize that H3O plus is the same as H plus. I don't know which one are you going to write? The shorter one? I hope you write the shorter one. Okay. All right. And here, yeah. So here what we're saying is, hey, if you know the concentrations of the ions based upon this picture versus the neutral molecules in this picture, you can calculate the Ka for this specific acid. So here, why don't we just do that? Okay, let's do that. So with this picture, let's calculate the Ka for this picture. How many H pluses are in solution? How many in this picture, right here, just this one? 1. How many A minuses are there? 1. How many HAs are there? 1, 2, 3, 5, 6, 7. Okay, so 1 over 7, whatever that is the Ka for this specific acid picture representation. Versus if we tried to do it for this strong acid, there would be 1, 2, 3, 4, 5, 6 H pluses, 1, 2, 3, 4, 5, 6 A minuses, so that's 36 in the numerator. But then what is in the denominator? 0. And that is a, like, not a real number, or what is it? If you divide by 0? You can't do it, right? But let's say, what is the limit? As we approach 0, this number would approach infinity. So it's essentially infinite. That's what that's saying. So that's why we don't have Ka values for strong acids. But we do for weak, because there is a number in that denominator. All right, so that's weak acids. All right. So here is a chart of a bunch of different weak acids. So that Ka value tells us the magnitude or how much products we have in solution. So remember the products. H plus is in the product on the numerator in our Ka expression. So the larger K is, the more acidic the weak acid. The stronger the weak acid, the larger your Ka value is. This is the same idea from chapter 15. It's nothing new. Because we said when K was big, there was a lot of products. It's the same idea, but these Ks are a lot smaller. That's what you see here. Okay, so what we see with these different K values, so chlorous acid, it's still a weak acid. Its Ka value is only like 0.1 versus, or 0.01 versus something like phenol. This substance, its acidity, there's not a lot of H plus freely floating around in solution because its Ka is so small. And what I have highlighted in red here is which hydrogen pops off, the proton that pops off, the most acidic proton. This is a really useful skill to recognize when you get to organic chemistry, because oftentimes understanding the pKa's of hydrogens, very important when trying to predict mechanisms, because a lot of reactions are very similar to acid-base reactions that we talk about in this class, but with organic chemistry, it's the most reactive hydrogen in molecules are typically the most acidic ones. So you're constantly looking at pKa values. And those values are what you're going to see in textbooks. But recall what pKa is. That P just means negative log of the Ka value, and I have that down here. And so it's the same idea here. So you might see, oh, the pKa of phenol is like negative, or sorry, the pKa of phenol is like, I don't know, like 9 something. That's not a very acidic proton. That's what it's trying to say. So what we see here are the stronger weak acids. So hydrogens, protons that pop off easily, donated easily, have high, large Ka values, so a small negative exponent, or, and it's often easier to read it this way, they have small pKa values. Because here, if we calculate the pKa of chlorous acid, let's just do that. just for fun. So pKa for that chlorous acid is -1 E -2. Oh, it's just 2, right? pKa of 2. Oh my gosh, non-real numbers. What the heck? What am I doing? -log 1 E -2. It should be 2, right? Yes, 2. pKa of 2, 2.00. Versus phenol, -log of 1.3 E to the -10 is 9.89. All right? So higher the pKa, less acidic that proton, lower the pKa, more acidic, and Kas are reversed. Larger the Ka, again, it's the same idea from chapter 15. Big Ka, lots of products, more acidic. Small Ka, not a lot of H+, not so acidic. All right, so there we go. All right. Okay. So now let's do calculations. Yay. So it's ice tables galore. There is essentially 2, maybe 3 types of questions I can ask regarding weak acids, weak bases, and ice tables. And it reflects exactly what we learned in chapter 15, right? I gave you a reaction, and I could do one of essentially 2 things. If I gave you the equilibrium, I could give you the initial concentrations and the final concentrations, and then you would go ahead and calculate K. I think that's what this is. That's what this one is. The other alternative was I give you the initial concentrations, I give you K, you calculate equilibrium concentrations. So those are the 2 types of questions. It's the same thing here. The only difference is that instead of giving you equilibrium concentrations, I give you a pH. Because pH tells you something. If you know the pH, you know the H+ concentration, but the tip is here is when you're given the pH, that H+ concentration is always the H+ at equilibrium. Always. 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 So if you're given a pH, that H+ value goes into the equilibrium line. So if you do your ice table and you see that H+ is X, you know what X is, and you can just fill in everything else. Do you see how that's analogous to chapter 15? I hope so. Okay, so let's do it. We have a solution of formic acid. You don't find pH, you measure it to be 2.38. Because if you find a pH, it's like you misplaced it and you found it. No, you measure it. You use a pH meter and you measure it. So give yourself more credit. That's just my pet peeve about lab reports. Back when I used to grade lab reports, I don't do that anymore. Your fine TAs do that, but that was a pet peeve of mine when students would say, I found the temperature of the room. I'm like, no, you didn't. You measured it. Anyway, so let's put this together. We have a concentration. We're given a pH. Let's calculate Ka. So let's identify this concentration, 0.10 molarity. And I'm going to just tell you, we're going to do an ice table. This concentration is going to go where? This 0.1, formic acid. The initial line. It's going to go in the initial line. So 0.10 is going to go there in the initial line for formic acid. What about the rest of the stuff? This is the same ideas from chapter 15. 0 and 0, very good. What do we do next? The change line. So which way is this reaction going to go? Towards the product. So it's going to be minus X under formic acid. It's going to be plus X, and then it's going to be plus X. And so at equilibrium, there's 0.1 minus X formic acid, so HA. You can also, oftentimes when I do weak acid things, I just do the generic, like HA plus H plus A minus, because I'm lazy. And we'll see that all weak acids follow this type of thing. All right, so there's that. At equilibrium, H plus is X, and then at equilibrium, A minus is X. So let's put together our Ka expression. What is it? X squared over 0.1 minus x. That's what we're trying to calculate. Do you see how I got that? It's products over reactants. Okay, same stuff from the previous chapter. The only thing now, the only piece of information we didn't use yet is the pH. Okay? So this value, remember what I said, the pH is always describing the H plus at equilibrium. So this right there, the H plus right here, X, H plus is X. All right, so if we get the H plus concentration, it's equal to 10 to the negative 2.38. That is equal to X. So just plug that into that expression, and that's it. But I'll do it. I'll do it. So I know what X is. That's the big idea here. And do you see how it's very similar to chapter 15, where I give you initial concentrations, I give you like one piece of the equilibrium, like concentrations at equilibrium, and you can fill in the rest of the table. And then plug it into Ka. It's no different. Honestly, I think it's easier because acid dissociation, these reactions, always follow the same thing. It's always X squared over something. Always. Okay, so I'm just going to plug those in. So Ka is equal to that 10 to the negative 2.38 squared over 0.1 minus 10 to the negative 2.38. I mean, I can get the concentration. I'm just lazy. And so when you plug that into your calculator, well, this concentration is 0.00417 molarity H plus. I just don't want to write all those zeros. And so when you plug that in, you get 1.8 times 10 to the negative 4. All right. Let's check our work. Okay, so this is formic acid. You can look up formic acid's Ka. So I'll show you what formic acid's Ka is. So here, if you look at the overview sheet for chapter 16, I have tons of these ice table problems. Okay, and you'll see, like, I'll have 3 in a row that are exactly the same. All you do is change the initial concentration, and you do the same exact calculation. So anyway, formic acid on this table is right here. Is that what we got? Yay! Doesn't that get you excited? No? Doesn't get you excited? So if you went ahead and calculated, if you made this solution, right? If you made that solution, put 0.10 formic acid in water, measured its pH, and you get 2.38 based upon this equilibria, that's what the Ka for that specific substance is. I think that's kind of like a beautiful thing, that Ka, it's like an intensive property to your specific to formic acid itself. Okay, I'm impressed. I don't know about you. Maybe you're secretly jumping with joy. Okay, here's the other type of question. I give you initial concentrations. I give you Ka. You need to give me equilibrium concentrations. This oftentimes, when we did it in chapter 15, required you to use the quadratic formula. The nice thing about acids is that typically the dissociation is really small, so we can usually almost always make an approximation, almost always. So I will show you, I'll do the whole thing. So I want you to calculate pH and percent ionization. Let's do pH first. They use the same exact numbers, but remember, pH always describes the H plus at equilibrium. All right, so ice table time. So, and here you see I just use a generic HA to H plus A minus. So if we look at this, we have 0.3 molarity acetic acid. So where does that go? Goes into our initial line. So it goes 0.3 whatever, right there. Our H plus and A minus are 0 and 0. What's next? Minus X, plus X, plus X. And then we have 0.3 minus X, that's HA, X, X. It's literally the exact same. And you will see this often with weak acids. That's why I'm saying it's easier, because they all follow the same form. So what we see if we set up our Ka expression is equal to x squared over 0.3 minus x, and since we are given Ka, it's equal to 1.8 times 10 to the negative 5. We can solve for x. You can do it two ways. You can do it using the quadratic. Do you want to do that? No, I don't want to either. So what's the next valid approximation that we can make? Is K big or small? It's pretty small. So are we going to make that much product? Is X going to be really big? No, we're not going to lose that much. We're not making too much of this because Ka is small. So that means if X is small, this 0.3 numbers is not going to change that much. So my approximation here is that that whole denominator is pretty much 0.3 or 0.300 if we take it out to more sig figs, but I'm being lazy. Okay? That's nothing new, right? Like you remember this from chapter 15, it's like nothing new. But I'm going to prove it to you. If we do the quadratic, and we calculate what x is, we get something. If we do the approximation, we'll get another number, and they'll be the exact same. So I'll bring up Wolfram alpha because I'm lazy. Okay, Wolfram alpha, let's go. Oh, it's already in there. Okay, so there it is. So x squared divided by 0.3 minus x equals Ka, right? Yes? Okay, go. Okay, someone write that number down. Write that number down. 0.00231. Write it down. So that is the quadratic. It solved the quadratic for me. Nice. Okay, now let me just simplify it, and I'm removing the minus x part. Boop. Let's see what the number is. So now it's just a simple like add, subtract, take the square root. That's the number. 0.00232. So it changed in the third sig fig. It's not a big difference. It's not, actually, if you calculate the pH I think is exactly the same. Right? It's not even within the realm of error within there. Okay, so we got the numbers there. Did I even write this down? I don't even know. I don't know. Yeah, it was with the quadratic, we got 0.00232 molarity, and with the approximation, we got 0.002. No, the first one was 1, and the second one was 2, right? That's what it was. So we have x, but what does x mean? See, that's the difference between math and chemistry. We got to think about what these variables mean. X is what? It's H plus at equilibrium. Is that the number we want to get to what we want pH, right? So this is the number that we plug into our pH equation, all right? And so what we get, the pHs for both of these, if we do quadratic versus approximation, I'm assuming it's the same number. Maybe with rounding, not 0.00231. So this one is 2. How many sig figs? Probably 3. No, it's actually only 2 because Ka is only 2 sig figs. So 2.64 for the quadratic. And then the other one is, for fun, is 2.63. Yeah, it rounds down. Okay. So on an exam, there will never be two options that close together. So that's what I'm saying, that the approximation works fine to get you close enough, right? Because like the answers are going to be off different by like whole pHs, not by fractions. Yes, question. Usually there's a big enough tolerance that you can, but you have to recognize when you're allowed to use the approximation. You can't use it all the time. Like if K was bigger, you can't use it. You can only use it when it's fairly small like this. With mastering, there's typically a tolerance. So in this case, yeah, if you put 0.64 versus 0.63, it's probably gonna mark both correct because that's just like within rounding error. But honestly, I would just stick everything to Wolfram alpha. and just solve it the whole way. That's what I would do. Because it's just homework, right? Okay. Wolfram alpha is your friend. And oftentimes what we'll see when we do the next question, I'm going to use the exact same thing. I'm just going to change that 0.3 to something else. And I'll change the Ka. And that's essentially the same equation over and over. All right, so those are our pHs. It's, acidic. Now this last part, what is the percent ionization? This is another way to basically describe how this substance is ionizing in water. So how we calculate percent ionization is you take the ratio, basically this X term that we got, H plus concentration, over how much HA we initially started with. So that's 0.3, and we're asking ourselves how much of it became the conjugate base, or how much acid was produced. So to calculate percent ionization, you just plug in those numbers. We already got, so that H plus at equilibrium is X. So that percent ionization is the number we just got, 0.00232 over how much we started with, so 0.300 times 100, it is 0.78%. So a tiny bit, just barely a percent. If you put, is this acetic acid? If you put acetic acid in water, less than 1% of those acetic acid molecules actually go on to become full-blown like H pluses. At this concentration. I'll mention that, at this concentration. Okay, because percent ionization changes based upon our initial concentration. That's our denominator. And so you'll see that percentage change. You can do this calculation for any concentration. And that's a fun experiment, or thing that you can do on your own. Okay, which one's harder? This one or this one? Type 1 or type 2? 2, 1, you don't know yet. You don't know yet. Just do a bunch of practice, okay? Recognize that I have to give you two pieces of information, essentially, here. I have to give you initial, and I have to give you like a Ka, I have to give you a Pa, I have to give you two parts for you to calculate this. All right, so, so let's look at polyprotic acids. The idea here, we can actually take off multiple H pluses, right, if this was a neutralization reaction. But those different acids, those different protons have a different acid strength, and that's reflected in the Ka values. So what you'll oftentimes see for these polyprotic acids is that the first proton pops off the easiest. It's the strongest of all of them. And then as you take off subsequent H pluses, the Ka gets smaller and smaller and smaller. So those protons become less acidic. The idea here is like, if I have H2SO3, like sulfurous acid, if I take off one proton, what's left, HSO3 minus, is already negatively charged. So to take off another H plus, there's already high attractions there. It's difficult to take that second one off. And so that's why you see those K values decrease as we go across. It's harder and harder to take those off. So thinking about this, which of these three substances that I have listed here is a weak acid? HSO4, HSO4 minus, HO4 2 minus. Which one's a weak acid? Is H2SO4 a weak acid? No. It is a strong acid. So if you look at this chart, see how it just says it's large? That means that it's a strong acid. So no. Is HSO4 minus a weak acid? Yes, so HSO4 is represented by this number. That's the second hydrogen popping off. I'm essentially asking, how well does this hydrogen right there pop off? Okay, so yes, this one is a weak acid. Is SO4 2 minus a weak acid? This one's kind of a trick one. No. What's the giveaway? There's no hydrogen there. Yes, they're all like the same substance, right? Like H2SO4, HSO4 minus, SO4 minus. Only one of them is actually a weak acid. SO4 2 minus is better known as a base instead. It will take, it'll accept protons, but it won't give up any because it literally has none. Okay, all right, yeah, so that one's not. Okay, which is the strongest weak acid on this table? Which one? What are we looking for? A large Ka value? Okay, so which one's the largest? So sulfurous acid. But note how sulfurous acid has two numbers associated with it. The first one is the first, like the H2SO3. The second number is referring to HSO3 minus, that second proton. So the answer here is H2SO3, not this one, because it has a smaller number. Okay, which is the weakest acid on this table? Which one? So you're only looking at these ones. You want to look at all of them. All of those numbers represent something. Phosphoric, but it's the third one. So the problem is it H3PO4 that we're indicating is a weak acid, or the weakest weak acid? No. We need to figure out what substance Ka3 represents. And this is kind of difficult. So we know that it's this third one. So I think a good way to represent this is if we write the subsequent, yeah, question?
Why is it
Oxalic. Oh, is it? Oh, yeah, it is. That is bigger. It is bigger. Okay, let's do this a little bit more carefully. I don't think I even have an answer written down here. Okay, let's go through all these. So this number is to the -2, that number. Yeah, so actually oxalic acid, this one is the strongest. You guys tricked me. Yes, that one is the largest. Do we see that now? Yes? Did I make a mistake? Is there like another one that's hiding? Wait, why don't I say sulfuric acid? It's strong, yeah, it's strong. It's a strong acid. I'm asking for the strongest weak acid, yes. So very good. The strongest weak acid is actually oxalic acid. So it's H2C2O4. It's the first proton. Okay, so let's go back to the weakest weak acid. So I think the way that we can clearly represent what that Ka3 represents is write the subsequent Ka1, Ka2, Ka3. So the equilibrium for popping off each proton one by one. So the first proton, Ka1, involves the full acid, H3A. So I'm going to just call phosphoric acid H3A. Is that okay? Can I call it that? Okay. Because the 3 indicates there's 3 protons. So what's the product if I pop off one H plus? H plus what? H2A minus. That's Ka1. They don't all pop off at the same time. Okay, so let's write Ka2. Ka2 involves, we take the product in the last one and we pop off another proton. So Ka2 involves H2A minus equilibrium, H plus what? HA2 minus, that's Ka2. Now the last one, Ka3, I hope you can tell how to write now, is HA2 minus, pop off a proton, this is H plus A3 minus. So what substance is the weak acid related to Ka3? It is HA2 minus. It's this one. Right? Because oftentimes I think the biggest mistake is if I say Ka3 for phosphoric acid, students will think that is associated with PO3 or PO4 3 minus, so with all of the hydrogens off, but that's not an acid. That can't donate like protons because there are none. Right? So that's the tricky part. All right? Comes with practice, I promise. Okay, so there we go. It's HPO4 2 minus. That is the weakest acid on this table. And again, I think if you were to mess this question up, that one, the weakest acid, I think half of the wrong students would say H3PO4. They would say like the full the full acid, not the third dissociation one. Or they would say PO43 minus, which isn't even an acid. So you've gone too far, essentially, within that. All right? Okay, so if I point to any one of these Kas, you should be able to write the K expression, the full-blown chemical equation for any of them. Okay, I don't expect you to memorize them, but you should be able to like come up with it on your own, even if it requires you to like write it out subsequently like this. Honestly, this helps me. This helps me like figure out how many protons I've taken off. Okay, so there we go. All right, so that was weak acids. I'm gonna tell you weak acids are easier than weak bases. Bases suck because even when we were doing pH calculations, like if we put sodium hydroxide into water, you had to calculate OH minus concentration, then you had to calculate POH, then you had to go to pH. It's the same idea here. We use the same process as acids. It's just a little bit, sometimes it requires an additional step because we need to use a Kb expression. A Kb expression is different than a Ka expression, and it's hard to, sometimes it's hard to navigate. So a Kb expression describes a substance behaving like a base. So oftentimes we need to put water in there. We have to, because B, to act like a base will accept a proton, right? It's a proton acceptor, not a donor. So we need to take a proton from somewhere. Where is it going to come from? It's going to come from water. When this B takes an H+, you make its conjugate acid, Hb plus OH minus. Because there's free hydroxide, that's what makes this base basic. All right, and the idea here is that, you know, in Chem 1210, when I told you guys to memorize weak bases, we only asked you to memorize one, NH3. In reality, there are tons of weak bases, okay? But they all have something in common. Either there's like a nitrogen on it, like ammonia, so it looks like ammonia, or it's the conjugate base of one of our weak acids. So that's the idea there. All right, so let's write the Kb expression for this. What goes up top? Product, so Hb plus times OH minus over B. Do we put water in it? No. Okay. So if you look at a list of Kb values, the larger the Kb, the stronger the weak base is. Meaning, if Kb is large, there's a lot of OH minus present in solution. Okay, the larger that Kb value is, all right? So in this reaction, NH3 is your base, and which is our conjugate acid? NH4 plus, that's our conjugate acid. We need that water there to show that NH3 is gaining a proton, and there's our Kb reaction. So let me just quickly show you some Kb values. This is in the chapter 16 overview. This is just straight from the book. These are the Ka values, but here are some common Kb values. So kind of the reoccurring trend here for these weak bases are, see how they have nitrogens in them? Okay. And you can see these Kb values. So which one of these is the strongest weak base? Which one is the strongest weak base? What are we looking for? The largest Kb. So the largest Kb, this one is to the -4, that one. So I think it's this one, ethylamine, that one? No? Is there one that's smaller or bigger? No, that's right. Right? Okay, I don't know. Okay, so that's the strongest weak base. Which one's the weakest weak base? Which one is really crappy at making hydroxide in solution? Aniline. Very good, because its Kb is small, so there's not a lot of product. Okay, all right, let's go back. All right. All right, so I mentioned, you know, that table had a bunch of bases, neutral bases, okay? The kind of reoccurring theme was that there was a nitrogen in it, in the substance that made it basic, and they had appreciably big Kb values. So that's the first type. The second type of base we can see is actually a conjugate base of a weak acid. Not a strong acid, but a weak acid. So for example, so here are some neutral weak bases, but something like hypochlorite, which comes from the acid hypochlorous acid. If we pop off that proton, hypochlorous acid doesn't give up its proton very easily. I mean, it's an acid, but it doesn't give all of it up like a strong acid. It can take back that proton just as easily in water. So it actually makes hypochlorite ion, that anion, a weak base as well, because it's not so great at giving up a proton. It's also not so great at, or it's like kind of mediocre at giving up a proton, but it's also mediocre at taking back that proton. So the idea here are that weak acids, the conjugate is a weak base. So for example, HF, that is a weak acid, right? And if we write its conjugate base, F minus is also a weak base. The beauty here is that we can calculate Ka and Kb values for any of those substances using our Kw expression. So we only actually need one term to essentially fully understand a system containing containing HF or its conjugate base. All right, so side note here. So all of these things are weak bases. What you recognize or should see is that some of them, the ones that are conjugates of a weak acid, are an anion. They're an anion. So for example, carbonate here, carbonate ion, it actually has a pretty large Kb value. It's pretty basic. Carbonate, so like carbonic or like sodium carbonate, or even sodium bicarbonate, which is baking soda, is basic. The problem is if we want to use carbonate ion, can you just go to the shelf and grab carbonate ion from the shelf? No, you can't just get a cation. So if I wanted to add carbonate to something, I have to add its salt, its neutral salt. So recognize if I wanted to add carbonate to something, I would need to take the bottle of sodium carbonate and recognize when I take that solid and put it into water, it makes carbonate, which is basic. So if I put sodium carbonate in water, it will turn it basic. I think that's one of these up here somewhere. And we'll see it that it turns basic, that I can't just get just a single ion and put it into solution. All right. And that will take us to predicting pHs of different salts. Okay. All right. All right. Last idea here, and then we'll do more calculations. So let's consider the relationship between Ka and Kb for conjugates. This is very important for weak base calculations. So let's look at NH3, the acid, or sorry, the base, and NH4 plus, its conjugate acid. Here are the K values, if you look it up. So if you look up the Kb value for ammonia, because it's a base, B stands for it's behaving like a base, is this number. For NH4 plus ammonium, its Ka value is that number. So that's ammonium behaving like an acid. Let's write those expressions for both of them. So Kb is ammonia behaving like a base. So what is it going to do? NH3 behaving like a base is going to do what? Is it going to donate a proton, or is it going to accept a proton? Accept. So its product is NH4 plus aqueous, and then what else? OH minus. Yeah, because it accepted a proton, but from where? Where did it take that proton? It took it from water. Okay. Now let's write the Ka expression for its conjugate acid, NH4. So NH4 behaving like an acid is going to do what? Is it going to accept a proton, or is it going to donate a proton? Donate. Acids donate protons. So what are the products here? NH3 and H plus. That's the Ka expression. Add them up. What do you get? Add those two reactions up. To-do. Okay. Boop, 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 boop. What is that? Water. Yes, water. So the idea here is the product. So when we add reactions, what do we do the K's? Do we add them? No, we multiply them. So what this is saying is that Ka times Kb equals Kw. Isn't that water? H2O dissociates to H plus to OH minus. That is the auto-dissociation, auto-ionization of water. So that's what this is saying. All right, when we add those two things up, H2O, and sometimes you just got to do it for yourself to clearly see it. Whoops, that's not right. Okay, H plus plus OH minus. This is equal to Kw. So the big idea here is that for any acid conjugate base pair, Kw equals Ka times Kb. And we're going to just say it's equal to 1 times 10 to the negative 14 at 25 degrees Celsius, because 99% of what we're doing is at 25 degrees Celsius. Okay, so that means if you throw, is it the next example that? No, it's not. If that means if I throw in sodium fluoride into solution, and I only give you an HF Ka, you can figure out what the Kb is for F minus by just manipulating Kw to get Kb. That means I don't need to give you Kb directly. You can just look at the Ka for the conjugate acid. All right. So Kas and Kbs are related. We know that when you multiply them, it's equal to Kw. So how this works out is that the Kas in one direction are the opposite for Kbs. So because Kbs, you're like adding protons back. So for ascorbic acid, like the other way, this would be Kb1, this would be Kb2, going the other way, all right? But you have to do the 1 times 10 to the negative 14 over that. So Kb in these examples are Kw over that appropriate Ka. So let's calculate Kb1 and Kb2. So for this substance, Kb1 is equal to, what are we doing? Carbonic acid. So we're taking this number. We're taking Kw, so 1 times 10 to the negative 14 over 5.6 times 10 to the negative 11 equals something. All right, equals 1.8 times 10 to the negative 4. All right, and then Kb2 is like the same thing, except we use Ka1 because that's adding the second proton on. It's essentially the opposite of taking that first proton off. So do recognize this, that each of these K reactions corresponds to a specific proton being added or removed. So this would be 4.3 times 10 to the negative 7. And so that's Kb2, I'm sorry. So this value is 2.3 times 10 to the negative 8. Okay. So based upon this Kb1, Kb2, so Kb1 is referring to CO3 2- is behaving like a base because it's kind of on the opposite end of this. We've already taken everything off of carbonic acid. Now we're putting them back on, those protons. And so Kb2 is referring to HCO3- behaving like a base. We're putting that last proton on to make carbonic acid as our product. So of these, which is the stronger base? Carbonate or bicarbonate? Carbonate, because this is Kb1 and it has the larger value. Right? So do you see, because of like how these inverses happen, right? This is kind of showing the smaller the Ka value, the weaker the weak acid. Because if we look back at the Kas for carbonic acid, which one is the smallest one? Ka2. So that's saying HCO3- is the weakest acid. So therefore the opposite is true. Carbonate, its conjugate base, is the strongest base. And it's because of how those numbers work out. Okay, so are we doing calculations yet? Oh my gosh, one more. Okay, Ks and Kbs are related. Identify and calculate the Kb for the strongest base in this table. What? They only gave me Ka values though, not Kb's, right? In your mind, you think, okay, strongest base, largest Kb value, but they give me Ka's. So what am I actually looking for? The smallest Ka value. So which one's the smallest Ka value? So let me just write what I just said. So if we want the strongest base, we want the largest Kb value, but since they give me Ka's, we want the smallest. So which one's the smallest Ka? Is it phosphoric acid again? Yes, it's this one. But now we need to identify, so I can, go ahead, turn this into Kb, and then turn this into pKb. And I think that number is, so Kb is like 2.4 times 10 to the negative 2, so pKb is 1.6. But the hard part is we need to identify it. So it's the third Ka of phosphoric acid. So what is the strongest base form of phosphoric acid? It would be the phosphate. The phosphate ion, this one, is the strongest. Because you're looking at the conjugate base of that third acid reaction. I'll go back once you write this down. I'll go back to those equations that we wrote before, because I'm lazy. I'm going to go back real quick. These equations, these ones, remember? Remember what these Ka expressions, this was for phosphoric acid, that this proton pops off the easiest. Ka1 was the largest. Ka3 was the smallest, meaning that this proton didn't pop off very easily. So since this Ka is the smallest, Kb is the largest, but Kb is actually referring to the product, A3 minus, which is phosphate 3 minus. That's how that all works. Yes, it's all very counterbalancing with acids and bases, but these numbers all are related to the same foundational information, but it can be confusing as there's a lot of reversing involved. All right, so Kb's, Kas are related, so that's how we read these tables. So recognize I can give you an acid, or I can give you a conjugate base of an acid, but all the information we need is still on this table. So let's look at this. Let's look at this one. So let's calculate the pH of this substance with the given Kb information. So there's a lot to unpack here. We're given a concentration. We want a pH. The piece of information that we're missing is like a K value, but it's saying, hey, figure out what it is. Figure out what the right one is. That's the problem. So the first thing here is we need to identify what substance are we dissolving in water. This is a salt. So there's C5H5NH plus and Cl minus. That's what that substance is. It's analogous to NH4 plus and Cl minus, something like that. Okay, so right here, I give you Kb values. So I see that this substance is the conjugate acid of pyridine. Do you see that? Okay. So this substance, that cation, is pyridine with an extra proton on it. So when I put this substance in water, is it going to behave like an acid or a base? If it was just pyridine, it would behave like a base, but there's an extra acid, like an extra H plus on it. So it's actually going to behave like an acid. It's going to behave. So essentially what you're seeing right here is BH plus, and versus like just this would be B, this is BH plus. That's the conjugate acid. So we need to actually convert these Kb reactions, or Ks, these Kb's to Kas, because the substance we're putting in water is actually behaving like an acid. So let's do that. All right, so Kb, this is actually an acid. It's going to do this. If it's an acid, it's going to donate that proton. So we want to convert that Kb to a Ka value. So Ka equals 1 times 10 to the negative 14 over that Kb value that's given. So 1.7 times 10 to the negative 9. So that number is equal to, oops, sorry, got butterfingers, is equal to 5.88 times 10 to the negative 6. All right, so since this substance is acting like an acid, I'm just going to write a generic acid equation. And we're going to do a nice table. I'm going to take that initial concentration that's given. So the new part is we identified that this substance was an acid. It's not a base. It has like a footing within the base realm. It's coming from pyridine, which is a base, but because there's an extra acid, or sorry, H+ on there, it's actually acidic. So I'm going to put that 0.10 concentration right there in our initial line. And I hope your brain is just auto-filling the rest. We have 0, 0, minus x, plus x, plus x. And so our equilibrium line is 0.1 minus x, x, and x. What do you think we do next? Plug that into Ka. So Ka is equal to x squared over 0.1 minus x. And that is equal to that number we just got, 5.88 times 10 to the negative 6. So this is the hard part that I think students is the hardest part, is, okay, you gave me these Kb values. Why do I have to convert it to Ka? Like, what is so wrong with taking this number and sticking it here? The reason we can't do that is that this substance is not a base. It's acting as an acid. So we have to write the acid equation. So we need to use a Ka value. A stands for, in Ka, stands for acid. All right, so what do we do next? Solve for x, and then x is H+ concentration, you get pH. And so what you get here is x equals something, I don't know. So you can do the quadratic or you can do the approximation, and you get x is 7.64 times 10 to the negative 4, and you get pH equals 3.12. This substance is an acid. It made the solution acidic. It's the conjugate acid of a weak base. It's an acid. It made the solution acidic. Let's pretend, okay, this isn't in your slides. I realized we didn't do a weak base calculation. Let's pretend you didn't put the weak acid conjugate in water. Let's pretend you put the base in water. So we're still working with pyridine. It's the same conditions. You put 0.1 molar, you accidentally grab the wrong thing off the shelf, and you put pyridine in water. Pyridine is a base. So it's going to behave like a base. So we're going to write the base equation. So we're going to use Kb. So let's do that. Let's just call this, see how there's no H on the back end? It's just neutral. So we will use Kb here. So let's write this substance behaving like a base. I'm just going to call it B because I'm lazy. So B plus water gives you, what are the products when B base acts like a base? BH plus OH minus. Okay, now we got to do a nice table. So what goes in the initial line here? 0.1. We don't have to put anything for water. It's not going to go in the equation. And then zeros over here. What's next? Minus x plus x plus x. So equilibrium is 0.1 minus x, x, x. So this is the Kb expression. So we're going to set up the Kb like equation. All right, so I'll just write it for fun. So Kb equals BH plus concentration times OH minus concentration over B, neutral. We don't add water. And so if you put in those numbers from the equilibrium line, you get x squared over 0.1 minus x. Does that look familiar? I hope it looks familiar. It's like the same freaking thing over and over. But the difference is in this one, because we put a base in water, we don't use Ka, we use Kb. That comes straight from the table. If I yell at you louder, will it go through your head? Maybe, I don't know. So we set it up equal to Kb, so 1.7 times 10 to the negative 9. What do we do next? What do we do next? Solve for x, but the thing is here, we need to be better than math people. What is x? Don't jump the gun. Look at the reaction. What is x? It's OH concentration. Because remember when we did Ka up here? X was H plus, because that was the reaction we were looking at. Okay, so that's the tricky part, all right? That's the trick. I know it's a lot. I know it's a lot. So go back, but these are all things we learned in chapter 15. It's not just, we don't just solve for x. We have to also think about what does that x mean. So when we solve for x, we recognize that this is OH concentration at equilibrium. It equals something. Are you going to do the quadratic here? You can, but you don't have to. You make the approximation, good, yes, and so you make the approximation and you get that OH is equal to 1.3 times 10 to the negative 5 molarity, and so after that you get POH and then pH. So that's the difference when working with just like a neutral weak base like that when you're given Kb. And so POH is 4.89 and then pH is 9.11. Okay, let's use our intuition. You added a base to water. The solution should, or the pH should go up. Did it? Yes, it did. Okay, so if you get something that's counterintuitive, try again. You might be using the wrong Ka versus Kb. Okay, all right. Let's keep going. Is that it? Yes. All right, now let's do the salt stuff. Do the salt stuff. And it's the whole idea is that the conjugates of weak acids or weak bases are also weak acids and weak bases. So basically the strategy here is if it's a cation, right? So these are salts, right? Salts always have a cation and an anion. If you have a cation, that is most likely where a weak acid will be. If you have an anion, that is most likely where a weak base. Did I get that right? Yes, a weak base will be. Okay? So what we're looking for are conjugates of weak acids. If the ions are conjugate of strong acids or strong bases, they will be neutral. They will be neutral. So like, for example, sodium chloride. Sodium chloride. Oh, I did not write, my mouth said one thing, but my hand said another. Okay, sodium chloride. Chloride, Cl minus, when it's attached to a hydrogen, is also known as HCl, which is a strong acid. NaOH, when it's attached to like OH, is a strong base. So when you mix those two things, you get a neutral salt when you mix a strong acid and a strong base. So that's something like NaCl. So NaCl in water is pH neutral. It won't change the pH at all. That's a little bit of a lie, but you have to take higher level chemistry to learn about that. So you won't learn about that here. So NaCl, when you put it in water, it will keep the pH of your water neutral asterisk. But there are other substances, like in this example, the one that we did up here, this one, where we had the conjugate acid attached to Cl. So this is an acid. It is the cation part of the salt. So if you're going to be seeing a cation, that's the most likely place a weak acid will be. And that weak acid will typically be a conjugate of a weak base. So here are some examples. Like NH4 plus is the conjugate acid of what base? NH3. So you're just ripping off that proton. you're telling it, oh, it's behaving like an acid, so you're ripping off that proton. Also, some of the Lewis acids we see, which we'll talk about in a little bit, are highly charged metal cations. Something like iron 3+ or iron 2+ also is actually acidic in water. It behaves like an acid. Anions, that's typically where your bases will be. All right, so something like carbonate, fluoride, acetic acid, acetate. Those are the weak base conjugates of weak acids. So they behave like weak bases. So you will find weak bases in your anions. So oftentimes, amphiolites, so things that where multiple protons can come off. Sometimes it's up in the air whether something's acidic or basic. You actually need to look at the Ka values. Okay. So, but then look out for pH neutral cations or anions. These are things that are conjugates of strong acids and bases. So sodium, nitrate, potassium, all those things will always be neutral because they don't have a weak conjugate at all. Okay, so, all right, so let's look at some examples. Let's predict whether things will be basic, acidic, or neutral. So let's go through these. So my first strategy is just break up everything into ions and look at the ions separately. So NH4 is NH4 plus and then NO3 minus. So look at them individually. Nitrate comes from nitric acid. Is that a weak acid? No, it's a strong acid. So nitrate is neutral, straight up neutral. It's not going to change the pH of the solution at all. But NH4 plus, is that a conjugate of something? It's a conjugate of NH3. So this NH3 is actually acidic. So that means this whole thing is going to be acidic. Do I have it here? Do I have it? Sodium chloride, yes. Ammonium nitrate, yes. Let's do it. Let's do it. Okay. Let's do salt first. Yeah? All right, so remember what this was? HCl. So this is the color of a acidic pH versus this one was basic. So what I said, sodium chloride. Same idea as potassium chloride here. They both come from conjugates of strong acids and strong bases, so they're not going to change the pH at all. So this is KC. I'll just pretend. This is KCl. Pretend it's KCl. So KCl, like sodium, the example I have up there, should not change the pH of the water at all. I don't know how much to add. Pour with confidence. Okay, don't mix with that. There's a lot going on here. Okay, so this is NaCl. Did it change? No. All right, this one is ammonium nitrate, NH4 NO3. Okay. How much do I add? Oh, wait. Okay. What color do we think it's going to change? The orange. Oh. Is that acidic? Yes, it is. And it's because NH4 plus is a conjugate acid of a weak base. Good. Okay, let's do another one. All right, so there we go. We did that one's acidic. We said that this one was neutral, right? Neutral, because K plus and Cl minus, HCl is strong acid. KOH, that is a strong base. So together they make a neutral salt. All right, NaF. So we have Na plus and F minus. Na plus, basic, neutral, or acidic. Na plus. It's just like K plus. It's actually neutral. So think NaOH is a strong base. So it's not going to it's a strong, I don't want to say, yeah, strong electrolyte. All right, so this is actually neutral, but then the important one is actually F minus. If we tack on a hydrogen on that HF, you ask yourself, oh, HF is a weak acid, so F minus is a weak base. Yes, so NaF should be not acidic, not quite acidic. So HF is an acid. They're a weak acid, so F minus is a weak base. So NaF should be basic. I don't think they gave me, oh, yes, they did. They gave me sodium fluoride. Right here. Okay. Ready? Wait, what do we say it is? Basic. So what color should it turn? Purple or whatever. Does it tell me how much to do? Probably. I have no idea. Okay. Okay. Sodium fluoride. I don't want to add too much. Fluoride's not very good. Is that enough? There we go. Did it happen? Is it basic? Yes. Why? Because fluoride, F minus, the conjugate base of HF, which is a weak acid. Okay. Okay, what's next? And this one's sodium bisulfate. Okay, well, this one's sodium carbonate. Okay. Sodium carbonate, Na plus, neutral, acidic, basic, neutral. But then CO3 minus, 2 minus, sorry. It's going to be basic because it is a conjugate of bicarbonate or carbonic acid. We've ripped a bunch of protons off of a what am I trying to say? Off of a weak acid, carbonic acid. Yeah, so I have sodium carbonate right here. Okay. Do you see how we got CO3 2 minus is basic? Because it is the conjugate base of a weak acid. So I got sodium carbonate right here. Okay. So what color is it going to turn? Purple. Because we are predicting it is basic. Is it purple? Yes, it is. Okay. How do we feel about that? How do we feel about identifying things? Okay, so I will point out that some metal cations are also acidic. So not things like sodium, potassium, lithium, not those things. I'm talking about like transition metals. Things that are smaller, the things on the left side of the periodic table, those ions tend to be big, but as we go further to the right side of the periodic table, they get smaller. And so when we have highly charged metal cations, they actually behave as Lewis acids, where they actually rob water molecules and they become solvated, and the bond is so strong that one of the hydrogens off of water pops off. So things like highly charged iron or aluminum are Lewis acids. So actually I want to do one. So you can see the Ka for different cations here. I thought was silver on here. Okay. Zinc, zinc on there. It's not that good of an acid. I'm kind of scared to do one because I don't know what color it'll turn. Okay, I'm not going to show one. But if we put some of these highly acidic cations into water, they would turn the orange color because they're essentially, those water molecules are more attracted towards the cation than when you have a really strong bond, one of those hydrogens will pop off, or those protons. So the trend that you see with metal cations is that the acidity of the cation increases, or the Ka increases, when you have a highly charged cation or the size is small. So what you see here, if you look at iron 2 and iron 3 has a larger Ka value. It's more acidic because its charge density is larger. So essentially what you're looking for is a high positive charge density, because when you increase size or, decrease size or increase charge density increases within there. Okay, so there's that. I want to do one more question. Yeah. And then we'll just do some practice problems tomorrow and then get into chapter 17. But let's look at these substances. It's just another way to word the same question. If we have 0.1 molar solution of a salt and it's neutral, what is the identity of that salt? Which one could it be? 1, 2, 3, or 4? If it's neutral, what do we think it is? So let's go through it real quick. I'll start with this one. Sulfate is the conjugate base of a weak acid. So this one's probably going to be basic. Also, Cn- is the weak base of a conjugate acid, HCN. So this is also going to be basic. Number 2, we already did this one. Ammonium will be acidic because it is the conjugate acid of a weak base, NH3. KBr is neutral. Yeah, see how I had to do it backwards. So we had to go through all of them. Because HBr is a strong acid. And then KOH is a strong base. So that's why it's neutral. So that is that. It's actually analogous to just saying NaCl or something like that. All right. Okay, that was a lot of information. We'll do a couple more practice problems on Wednesday and then jump into chapter 17.